Exercise 30. I'm redoing this one because the first time my computer froze up a ton and it was basically unwatchable, and also I forgot a part. And I like this one, so let's do it. So we're going to construct an increasing function. By the way, my arm is, I sprained my wrist, so we'll see how this goes. My writing might be a little sloppy. But anyways, let Qn be an enumeration of the rationals in the interval from 0 to 1. So we're first going to define f on our increasing function f on this interval, and then extend it. So define f on, let's say we just define it on the closed interval from 0 to 1 by f of x equals, then I should probably start a new line just in case. The sum from n equals 1 to infinity of 0 to the minus n times the indicator from 0 qn to 1 of x. So we want to make sure that this is a well-defined function and that it is increasing. So we're going to prove that it's increasing, and then once we prove that the sum converges at 1, it will follow that it converges on the entire interval. So anyways, first let a and b be in the closed interval with a less than b. We're going to prove that f of a is less than or equal to f of b. Then the collection of points n and n such that qn is less than or equal to a is contained in those points such that qn is less than or equal to b. Right? Because if qn is less than or equal to a, then it's less than or equal to b as well, because of the way that the inner inequality goes. And so f of a equals, I'm going to have to start another line again. Sum, actually, let's indent this a little. F of a equals the sum from n equals 1 to infinity of 2 to the minus n indicator qn1 of a, and that's equal to the sum over, I'm just going to write this as qn less than or equal to a. So this is the sum over all n in the natural numbers such that qn is less than or equal to a. To the n, and that's just by definition of the indicator function. But then this is certainly less than or equal to, actually it's strict inequality here, but whatever. Less than or equal to this sum, which is precisely f of b by our definition. Ugh, writing's all sloppy, but at least it's writing. Plus f is increasing on 0 to 1. Also, 1 is in qn to 1 for all n. So f of 1 is just, well, the indicator function is always going to evaluate to 1, so it's just this, which is equal to 1. So the sum converges at 1 and thus on closed interval from 0 to 1. Okay. Also, and this is more of a side note, 0 is not in Qn 1 for any n. No. Okay. So, see here. F0 is equal to 0. Okay. So here at this point, I don't think I'm going to be able to fit everything on this screen, so I might as well scroll down a little bit. And hopefully this won't freeze up like it did last time, because if so, that could make this really difficult. Okay, so let's prove that f is discontinuous on Q intersect, and here we'll just take open 0 to 1. The left endpoint 0, I don't think it's going to cause too much of an issue, but I think when I wrote this down, I made it in such a way that it kind of works nicely. So anyways, all we really need to worry about is discontinuity on this set. So trust me on that one. So let n be an n. I.e., let's choose some Qn in this set. Then for all x between 0 and Qn open, x is certainly not going to be in the closed interval from Qn to 1. So f of x is going to be less than or equal to f of Qn minus 2 to the minus n, because 2 to the minus n is the one that goes with the Qn term. But then what happens? We have the limit as x increases to Qn of, I forgot the argument here, but this should be the limit as x increases to Qn of f of x. This is always going to be less than or equal to f of Qn minus 2 to the minus n, which is strictly less than f of Qn. Okay, so what does that mean? So then f is not left continuous, and thus not continuous, obviously, at Qn. And this holds for every single Qn, and so here I'll just write it. Hence, f is discontinuous on Q intersect 0 to 1, because it's discontinuous at every single point in there. So now let's prove continuity on the irrationals. So to prove f is continuous, I'll just abbreviate like that, on the set open, we'll prove that it's continuous on the open set 0 to 1 set minus q. It's because, I mean, technically this is the complement of q intersect open 0, 1, because q intersect open 0, 1 is going to contain the point 1. And so when we look at the irrationals, we're not going to contain the point 1. So let x be in the set irrationals And what else do we want? We want epsilon greater than 0. Choose n, natural number, large enough that the sum from n equals n, capital N to infinity, of 2 to the minus n is less than epsilon. And this, not which is possible since the sum converges. So then choose, let's see here, delta equal to the minimum, the distance from this particular x to q1 all the way up through qn. Then for all y in this interval 0 to 1 such that x minus y in absolute value is less than delta, not we, but rather we have, because qn is not in this open interval for any n strictly less than n, what do we have? Scroll down a little bit more. F of x minus f of y equals the sum overall. Okay, so the sum overall, let's write out what I had. The minimum of x and y less than or equal to qn less than or equal to max of x and y to the minus n. So what is this? This is the sum over all indices little n such that the corresponding rational number qn is basically in the open interval between x and y. We don't know which one's larger, so I just put min of the two, max of the two. I probably could have said at the beginning, assume without loss of generality one of the two, but whatever, this will do. But then this sum, we know that none of these are going to be none of these n's are going to be strictly less than capital N, because all of we've kind of excluded those from our sum. Oh, and I should close this bracket, otherwise my LaTeX won't compile. Anyways, so this is less than or equal to sum from n equals n to infinity to the minus n, but hey, we chose that to be less than epsilon. So hence, f is continuous on 0, 1, minus q. So now we're ready for the last part of this proof. So so here, let me start writing. To extend f from 0, 1 to r. So let's draw a picture. And let's see here, my computer sounds like it's working really hard, so hopefully this will actually appear on the screen. But anyways, so far we've defined f in this box here. And there's really no good way to know what it looks like other than it's just some increasing set or increasing function, and it looks kind of fuzzy. And then let's see here, so somewhere in here we have a jump of 1/2, and somewhere we have a 1/4, a 1/8, 1/16, and so on. So there's a whole bunch of jumps in here, but we don't know where they are, and we don't know what this looks like. But we know that at 0 it's 0, and at 1 it's 1. And so we can just take this box, kind of translate it along the diagonal of the R2 plane. And if we do that, then since this function is continuous at the irrationals but discontinuous at the rationals in 0, 1, it should have the same properties on all of R. So now that we have a little bit of intuition on what this should look like, let's actually formalize this. Oh god. Oh, my pen died. Here, let me revive it real quick. There we go. Alright, to extend f from 0, 1 to r, let's put a comma here. For any x in r, write x equal k plus y, where k is in z and y is in 0 to 1. It should be clear that there's a unique way to write x in any of this form. You can do a proof of that if you want. I think it's clear enough that it doesn't require any other explanation. And let f of x equal k plus f of y. So this is literally exactly that picture we drew. F increasing... Let's actually use grammar here. Since f is increasing on the interval 0 to 1, it is increasing on R. Perhaps there should be something said here about the fact that you don't have like any kind of issues at the integers, because the integers are where you're gluing stuff together. But because f of 0 is 0 and f of 1 is 1, it should be kind of clear that there's that like the endpoints from each side sort of match up when you glue them together, and so it works out. Match up in the sense that they work well and they agree, but it's not continuous at the integers, because it's not continuous, because f is not left continuous at 1. Remember, you've got that jump. And so even though the two functions agree on the integers, you still have a discontinuity at the integers. So anyways, let's continue with this. Also, since f is discontinuous on 0, 1 r, you know what? Let's make this a capital F. Capital F equals this. Since lowercase f is increasing there, capital F is increasing there. This will just help us so that we're not using f to refer to two different functions, because technically they are different functions because they're defined on different sets, even though they agree on the interval from 0 to 1. Anyway, so also since f is discontinuous on this set, capital F is discontinuous on Q. And that's because if you take translates of the open interval 0, half open interval from 0 to 1 translates by the integers, you'll get all of R. You won't even have any discrepancies at the integers there. F is discontinuous on Q. Lastly, since F is continuous on 0, 1 set minus Q, F is continuous on R set minus Q. And there we go. So capital F satisfies all of the desired properties, and so we have completed the proof.